Hello everyone, we are Team Shoot for the Moon. Welcome to a presentation on our hybrid dust mitigation brush utilizing EDS and UV technologies. Our faculty advisor is Dr. Julie Lindsay. Our additional advisors are Dr. Michael Scheibel, Dr. Zach Sievers, Dr. Thomas Orlando, and Dr. Edgar Lightsey. My name is Ali Mahmoud, one of our team leads, and I'm excited to begin our presentation for you today. We're going to begin with an outline of our presentation. It will be broken up into 6 major parts: project scope and statement, where we'll talk about the antecedents to the project, our proposed system and its novel aspects, our designed EDS system, our brush system including human factors design and EDS and UV experimentation, our path to flight, and finally our most notable findings and conclusions, including future improvements. Moving on to our project scope and statement. Lunar dust accumulation poses both an operational obstacle and health hazard to astronauts. Prior solutions to the problem of dust mitigation were simple brushes. However, dust accumulated on these brushes due to electrostatic adhesion and rendered them ineffective. Our focus, as a result, is to mitigate lunar dust accumulation on astronaut suits through novel methods. This leads us to our proposed system. Team Shoot for the Moon proposes an astronaut-centric ergonomic brush system that electrostatically charges and repels lunar dust with UV and 3D EDS technology. Our proposed system requires a multi-stage dust mitigation process, that is, brushing dust from the astronaut suit, then using UV radiation to charge present dust particles, and finally activating EDS to repel the charged lunar dust. Our verification testing has successfully shown dust mitigation through effective EDS and UV implementation. This can be enhanced by component upgrades to allow for simultaneous UV and 3D EDS use. Novel aspects of our design include 3D EDS brush integration, 3D EDS and UV technology conjunction, and a lightweight mechanically simple brush design, all of which can be expanded upon further.
Hi, my name is Christina Paris, and this is a high-level look at our project timeline. Phase 1 involved researching EDS and UV applications, creating a preliminary brush design, and planning future experiments. Once these were finalized in Phase 2, we performed 7 sets of experiments which validated our dust mitigation solution in high vacuum conditions. Also in Phase 2, we designed, built, and programmed an EDS controller module and made significant changes to the brush's appearance with human factors in mind.
Hello, my name is Gabriel Rizzo, and I will be discussing the design, development, and testing of the EDS electrical systems hardware and software.
Hi, my name is Lin Zhang, and before we go in depth to the EDS system design, I'll give a quick overview of what EDS is, and then I'll throw it right back to Gabe. So the EDS system utilizes a patterned electrode network that emits a non-uniform electric field that produces a standing wave effect. The field produces force distributions comprised of Coulomb and dielectrophoretic forces distributed on the EDS surface. Charged and uncharged dust particles are affected as the field polarizes uncharged dust particles, and all affected dust particles with charge are levitated by the Coulomb force and swept over the surface by the traveling electric field.
Before we move into a more technical discussion of the EDS system, I'd like to briefly touch on our design process. You'll notice from the Gantt chart that work did not begin until the middle of July. This was several weeks after the beginning of Phase 2 of the project and was mostly due to member availability. What it meant for us was that we had to be a bit creative in how we organized our design process. The process was split into 2 stages. Stage 1 focused heavily on research, simulation, and preliminary design. Our objective here was to learn as much as we could about what the EDS system would have to do, create a useful set of requirements, and produce a preliminary design to address these requirements. Stage 2 was an agile refinement and implementation of the preliminary design. We built prototypes of hardware and software, ran them through a battery of tests, and improved them as needed. The agile stage of the design process in particular was useful in speeding up the design timeline. The EDS system is composed of several pieces of hardware and software, and the agile approach allowed us to refine these parts concurrently. And so what this meant was that even if we ran into issues in one part of the project, we were able to keep making forward progress somewhere. So that way the design was actually finished on time. The first product of the design process was a set of guiding requirements. These requirements were heavily informed by research into existing EDS approaches, as well as our expected use cases. We noticed several things during our research. First, High voltages are extremely dangerous and are to be respected at all times. Second, existing systems are often a collection of bulky and expensive lab equipment. Third, space is not a gentle environment. It is likely that components will break. This led us to our set of high-level system requirements, and these were high voltage safety, self-contained electronics, and a modular component design. We then developed system output requirements to ensure we could complete a wide range of experiments in the lab. First, we wanted the ability to generate several phases of completely arbitrary waveform shapes. Second, our signals were to have a maximum amplitude of 2 kilovolts and a maximum frequency of 120 Hz. This was above what we saw in most previous experiments. Finally, the EDS system was to be designed to drive capacitive loads. From our research into EDS theory, we found this was the most accurate way to design for the physical phenomenon taking place. The requirements were used to develop a high-level system block diagram. Functional requirements derived from the high-level requirements were condensed into functional blocks. These blocks were assigned a category, which is shown by the colors in the block diagram, and organized into modules representing physical allocation of functionality. This organizational strategy allowed different parts of the system to be developed simultaneously and reduce overall development time. This also led to two types of modules, the control module and the phase amplifier module. The control module contains digital circuitry to communicate with the command interface, in our case a PC, and to issue commands to phase amplifier modules. It also contains circuitry to monitor connected power supplies and perform initial low voltage regulation. There was to be only one control module in the EDS system. The phase amplifier modules contain the entire analog signal chain required to produce high voltage signals. This included a digital to analog converter, preamp, filter, high voltage power supply, and high voltage signal amplifier. All of the high voltage electronics are contained within the amplifier module for safety reasons. Additionally, each phase amplifier module contained input power and control signal isolation circuitry. Again, this was for safety reasons. There were to be up to 4 amplifier modules in the EDS system. I'll move on to discussing the hardware we've built now that we've gone through the important parts of the design. I'll start with the control module. This module contains a single circuit board, an image of which is shown on the slide. The board's design was driven by a need for speedy construction and ease of use, and this can be clearly seen by the perf board and socketed through-hole construction. You'll notice the red Arduino module on the left side of the board. It was selected to implement the control electronics as it is very easy to use and had a built-in USB port. Additionally, there are discrete 5-volt linear regulators for each phase amplifier module, and these are located on the right side of the board. Discrete regulators were implemented to reduce individual component heating and reduce costs by lowering the part specs required. This module will be refined and moved to a custom-made PCB in future work. Hopefully, from the renders you see on this slide, it is obvious that most of the electronics design effort went into the amplifier modules. Each phase amplifier module contained 2 circuit boards, one for the high voltage power supply and one for signal connections to the control module, low voltage signal generation, and high voltage conversion. The latter board is shown on the slide. The high voltage power supply board was to be stacked on top of the main board by mating to several header pins. These header pins are all on the right side of the render you see. Unfortunately, the specialty transformers needed for the high voltage supply board were unavailable due to ongoing part shortages, so none of these boards were built. Instead, high voltage cabling was connected to power supply connectors and a dedicated lab supply was used. We do hope to build several high voltage power supply boards in future work. The important design driver for this board was high voltage safety. Signals from the control module come in through connectors on the left side of the board. They are then fed through galvanic isolation circuitry. This ensures that control module connectors and human interface devices are never at high voltages, even in the event of a failure on the board. Additionally, you can see the board is split into 3 parts. The left side contains connectors and human interface logic, the middle contains low voltage signal generation circuitry, and the right side contains high voltage circuitry. This separation was done to physically distance dangerous voltages from control module and human interface devices. Finally, isolation slots were cut into the board around high voltage components. This is especially visible on the bottom image. Additionally, trace spacing and corner angle rules were set up in our board CAD program. These 2 measures were taken to ensure arcs and corona were highly unlikely to form even in an atmosphere where lower breakdown voltages are possible. Additionally, a compact layout was an important design driver for the amplifier module boards. This was because volume and weight are major constraints for space missions. A very compact board size of 85 by 30 millimeters was achieved by using primarily surface mount parts and by careful routing of traces. Signals on the board go from left to right, with connectors placed on the edges of the board. This allowed traces to be kept short and mostly straight, saving space. The control module and phase amplifier module boards were packaged into aluminum enclosures. Any connectors and human interfaces were mounted to these boxes. You can see renders of the control module enclosure on the top and phase amplifier module enclosure on the bottom of this slide. Ensuring useful human interfaces was the most important design driver for these enclosures. The interfaces were designed to be low clutter and easy to use. LED indicators were used to display important information to users. Specifically, this was module health, power supply status, and indication of high voltage outputs. Switches were included to allow manual control over important functions. Specifically, this was module enable and disable control, as well as physical disconnection of power to ensure safety. Additionally, low-cost hardware was an important design driver. Custom metalwork and connectors can be very expensive, so we selected commercial off-the-shelf parts as often as possible. We did, however, have to 3D print some custom connector housings to meet volume constraints. We also used common connector types as much as possible, again, to reduce cost. Specifically, we used DB9s for module interconnect, SHV connectors for high voltage outputs, and barrel jacks for power. The DB9 connectors will likely be replaced with mill standard 38999 circular connectors in future work for astronaut ease of use, as the current DB9s have very small screws that are hard to use with gloves. Finally, I will discuss the software written for the system. The diagram shown on this slide describes the structure and data flow of the software we wrote. You'll notice that there are two modules. The controller software runs on the Arduino in the control module and was written in C++. It is responsible for calculating output waveform voltages, controlling hardware, and communicating via call and response structure to any connected control interface. The interface software runs on any Windows PC and was written in C++, JavaScript, and Python. It is responsible for connecting and identifying an EDS system on the USB and running a web-based control graphic user interface. Several languages were used for this module to reduce time spent on implementation. It also made use of several open source software libraries. Additionally, a demo of the web graphic user interface was included as a part of our team's deliverables.
Hi, my name is Shuri Lum, and I'm on the Human Factors team. I'll be talking about how we came up with our final design. To create a sufficient design, we did our research by interviewing astronaut Dr. Stephen Robinson, read dialogues from astronauts in previous Apollo missions, and explored the XEMU. On top of that, we reviewed the NASA Standard 3000, the Human Factors Integration Design Handbook, and ergonomic requirements. To acknowledge the XEMU, our current design utilizes bristles and takes up more surface space than a paintbrush. To acknowledge our interview with Dr. Robinson, our current design has sturdy materials to help with muscle fatigue and has a strap to wrap around the hand for adaptability. We also considered how large the uniform is, as well as the flexibility for the various sizes an astronaut could be. The final design, as shown on the next slide, is intuitive, has a large surface area for efficiency, and considers muscle fatigue.
Hello, my name is Elle Smith, and I'll be discussing the final design of our system. The brush component of our final design closely resembles a thumbless glove which fits around an astronaut's hand. It features 3 bristle sections which sit on the palm. These sections are connected with fabric to allow the brush to both curve and angle with the astronaut's hand without complex mechanisms. The entire assembly secures onto the astronaut's hand with a Velcro securing strap to eliminate muscle fatigue due to holding or grasping the tool. The advantages of this design is that it creates an increased cleaning area on curved surfaces, reduces muscle fatigue, has a very low mechanical complexity, and is an intuitive design that's easy to use. In total, this is a mechanically simple, flexible brush designed for astronaut use. The EDS and UV systems are integrated in the following way. The brush bristle sections are interspersed with electrodes. These connect to SHV connectors located at the wrist. A separate brush storage and cleaning system contains a brush enclosure with the reciprocal SHV connectors, a UV chamber, and the rest of the EDS electrical systems and power. To explain how the system works altogether, here's an example of operations. The astronaut will start with a clean brush and use it until it requires cleansing, at which point they'll swap it out with another. The astronaut will place the dirty brush on the rack and plug it into the SHV connectors. A light will indicate connection. The astronaut will then take out a clean brush and start the system by closing the box and pressing the button. At this point, the EDS system and UV lamp will activate, dispelling the dust. Once completed, a green light will turn on, and the process repeats. Separating the brushing and cleansing functions and having a multiple brush system is advantageous to allow for continuous operations, because with the current stage of development, the EDS system requires about 10 minutes to operate.
Hello, my name is Zin Liu, and I will discuss the verification testing as well as the path to flight. For the verification process, the team used a custom ultra-high vacuum chamber, shown in the right, capable of operating in low and high vacuum. The experiment used lunar Highland simulant, or LHS-1, with different size distributions. We tested normal and sieved, or less than 45 micron size distribution of the LHS-1 simulants. The completed verification experiment included dust adherence, 2D EDS chip, UV, 3D electrodes, integrated bristles electrodes, and EDS system design verification. For the dust adherence experiment, the goal was to replicate the dust adherence problem within the brush bristles, which served as a baseline to assess effectiveness for later experiments. For this experiment, a dust cup was mounted to the bottom flange, and a brush segment was attached to a mounting bracket onto a translational feed-through at the top of the chamber. By repeatedly raising and lowering the brush into the dust pile for 10 consecutive times, the results showed that the simulants became lodged within the bristles as shown in the figure on the right. To verify the functionality of the EDS system, an interdigitated chip of alternating polarity with 1 mm of electrode spacing was designed and fabricated. The team first used a variac and a neon sign transformer to test the chip while developing our own EDS system. The neon sign transformer operated at 60 Hz with two-phase potential and 180 degrees offset. Testing in high vacuum, the chip demonstrated the capability to effectively remove dust. Initial dust movement was observed with approximately 1.5 kilovolts, and the majority of the dust were repelled with approximately 2.5 kilovolts. The generated electric field repelled the simulants in the upward direction, and the repelling action occurred within seconds when the specified voltage was reached. Additional tests were conducted to compare the effect of size distribution and thickness. The result indicate that the seed dust, or less than 45 microns, repelled more effectively and at lower voltage settings. In contrast, small dust piles remain when using the normal size distribution of dust. As for the thickness, multi-layer structure prevents the charged dust on the surface of the chip from moving, whereas a thin layer of dust was repelled more easily and effectively. The following video shows a highlight of one of the 2D EDS chip experiment at 8 times speed. Overall, the 2D EDS experiment shows effective dust repulsion. To verify that photoelectric charging can enhance the EDS performance by reducing the voltage requirement, a 172 nanometer excimer lamp was mounted inside the vacuum chamber above the dust cup. With only UV exposure, the dust pile showed minimal movement. However, when the EDS was activated with UV, the voltage needed to move and repel dust on the chip was reduced significantly. At 750 volts, or 50% of the required voltage for movement with EDS only, initial dust movement was observed. The addition of UV also caused simulants outside of the chip to vibrate, and the movement were more intense compared to the EDS only test. Further experiments revealed that there is no latency for UV to work effectively. At a constant voltage, the dust movement intensified within a second after the UV lamp was activated. To sum up, using UV and EDS simultaneously enhanced the overall dust repelling effectiveness. The 3D electrodes experiment consisted of using linear pattern electrodes with alternating potential. A series of tests were completed to find the optimal electrode diameter, spacing, and coating. In general, larger diameter electrodes allow higher voltage output, and tighter spacing reduces the voltage requirement to repel dust. Insulative coating on the electrodes prevents shorting when contacting the bristles. Illustrated in the figure on the right, smaller grains were mostly repelled off of the electrode surface, but the larger grains remained between the bristles. As for the dust movement direction, the electric fields tend to propagate the dust towards the tip of the electrodes. With UV, there was dust vibrating approximately half an inch from the electrode tip, which further support that the UV radiation can enhance the effectiveness of the EDS system. Overall, the 3D electrode experiment successfully demonstrated dust repulsion away from the electrodes. Integrated bristle electrode experiment was performed to verify the dust repelling functionality of the electrodes within the brush bristles. The result shows that the EDS caused the bristles to vibrate violently, and there was a significant amount of simulants being repelled out of the bristles at a rapid rate. Challenges occurred when implementing the UV radiation. The Thunderon bristles absorb the heat from the UV lamp in high vacuum, since the only way for the heat to be dissipated while in vacuum is through radiative cooling or conduction into the holder. The bristles started to deform after minutes of UV radiation. As a result, nylon bristles were tested. While nylon did maintain its structural integrity under UV exposure, the EDS performance was significantly reduced. The reduction in performance is caused by the low dielectric permittivity of nylon, which does not allow the electric field generated by the EDS to propel through the bristles. Therefore, bristle materials with high dielectric permittivity and low conductivity is desired in order to implement UV to further enhance the dust mitigation effectiveness. Overall, these experiments show successful dust repulsion, but bristle material improvement is needed to improve UV. Verification of the EDS electrical system was completed through a combination of computer simulation and prototype testing. With SPICE, simulation was used to verify power consumption and amplifier stability. The prototype was first tested individually, then as a combined system. The low voltage signal generation breadboard prototype was used for digital to analog conversion. The spec-down high voltage signal converter prototype was made for a low voltage topology test. 4 high voltage amplifiers were built to replace the variac and neon sign transformer. Thermal endurance test was performed for 40 minutes by setting the output to a high frequency square wave at maximum amplitude to pull as much power as possible. The initial experiment was performed without UV, and the result indicates that the square wave is more effective in repelling dust from the electrode surface. With 1.7 kilovolts at 60 Hz, there was significant dust movement. In comparison, the transformer needed 2.7 kilovolts for a similar effect. The dust in the center of the chip remained primarily due to the thickness of the dust layer. While EDS systems showed the promising results, it needs circuitry component upgrades for better performance. Due to schedule constraint resulting from shipping delays, the team was not able to test the EDS system with the higher grade circuitry component to support UV. Component upgrades will allow us to advance in TRL. Additional multi-phase testing are needed for determining the optimal frequency and voltage. For the EDS system, optimization is needed at the system, module, and software level. All electrical hardware and software should be radiation and space hardened, and more design work is needed for ease of use to the astronauts. Various circuitry improvements and thermal analysis are needed for consistent functioning product. Additionally, software should be streamlined and thoroughly evaluated for bugs and edge cases. For the brush system, modification can be made to increase the ease of donning and doffing the brush, and further design improvements can be made in compliance with NASA STD 3001 and HIDH. To effectively integrate the bristles and electrodes, the bristles should have high dielectric permittivity with low conductivity. As for the electrodes, thin, elastic, and coated materials were needed to be tested for extended use on the moon. To improve operational effectiveness, the EDS and UV should be combined as a single system. Therefore, it would be worthwhile to include UV back into the brush using emitters such as fiber optics.
Finally, we arrive at our findings and conclusions. Our designed 3D EDS system and testing showed successful dust repulsion from the integrated 3D electrodes and bristles. This is thanks to our effective EDS system design and combined use of UV radiation. This grades our proposed solution at a technology readiness level of 4. For human factors, our design is mechanically simple and has intuitive use for astronauts. Its separation from the EDS and UV electronics allows for a lightweight design that eliminates strain and enables a multiple brush rotation for continuous operation. Finally, some of our identified improvements include finding a bristle material of higher dielectric permittivity and low conductivity to avoid UV degradation, and modifying components of our 3D EDS for higher power output, all of which would increase our technology readiness level through component upgrades. Thank you for your time and interest in our presentation. We look forward to answering your questions at the NASA Big Ideas Forum.